Hey guys, Buildzoid here, and we're back with the Zombie GTX 970. This time we're taking a look at its memory power delivery instead of the core power delivery. Because yeah, I've made some upgrades to it. So let's get into it. Starting off with the capacitor mods that I've made. So here's how it used to look on the back, and then on the front there was just nothing. I didn't do anything to the front side of the card. Now, this isn't completely stock. So yeah, like you can see, I have like an extra capacitor here. I populated, I think like this used to be an empty pad, so there's like a few empty pads that I populated like over here. You can tell because like the soldering quality is not great, but it doesn't matter. It's about to get worse. So, and by not great, I mean like this is just way too much solder for this kind of connection. But also we have things like this. So yeah, this isn't like the comparison here isn't like completely bone stock memory power delivery on this card versus this. It's like very slightly upgraded versus this. So yeah, and the main difference is well, I had like an entire dead HD7 970 worth of 0805 multi-layer ceramic capacitors. So my goal was basically I'm gonna use every single one of these 0805 multi-layer ceramics that I have, and then I also decided to use these capacitors over here, these through-hole polymers. And these are just capacitors that I've used in past projects, but they do have like. I mean, I could have used salvage capacitors as well, but yeah, these are some that I've had for ages that I've used in past projects and decided to just ultimately use them here. Because for memory power delivery, I don't really see the point in using anything particularly fancy. So anyway, these are two 560 microfarad FP caps, so Nichicon aluminum polymers, and these are 5 milliohm ESR. This one over here is 560 microfarad, also Nichicon, but different series, and that's a 7 milliohm ESR. And you might be wondering, why did I put the higher ESR capacitor closer to the memory chips? Wouldn't it be better to use one of the lower ESR ones? And yes, but the thing is, the legs on these are already cut like to a shorter length due to the past applications of them. And I really wanted to connect to all of the capacitor pads over here. So I needed to use a capacitor that still had like more leg length on it, and so I went with this one instead of, I mean, I didn't have to, but I wanted to, so I went with this one. I don't think 7 versus 5 milliohm ESR is really going to make that much of a difference with aluminum polymers. So yeah, I don't like, technically, like, these might be better, but I think it in this scenario, it actually just doesn't really matter. And then for the multi-layer ceramics, I mean, I basically added a multi-layer ceramic to every, every existing 0805 basically got another 0805, right? So you can see here. This one didn't because, well, there's no space, and I didn't feel like doing hot air for this. Like, I could have populated this. This is actually, pretty sure this is padding for an 0805. I just didn't feel like dealing with hot airing that into place, so yeah, I didn't do that. Because, like, technically you can use a soldering iron to get a 0805 onto these kinds of pads, but it always ends up lopsided unless you, like, go out of your way to really clean the pads, and I don't like it. So, yeah, left that unpopulated. I don't really think it matters that much. Anyway, yeah, you can see here, like, extra, like, I had literally an entire dead HD7 970. And I'm pretty sure from the factory, the HD7 970 actually comes with more multi-layer ceramics than a GTX 970 does for like output filtering, because there's a whole bunch of multi-layer ceramics directly behind the core, and then right off the vCore VRM, right? So in front of the vCore VRM, there's just like a whole bunch of multi-layer ceramics. And so, though funnily enough, the AMD configuration for multi-layer ceramic capacitors for the memory chips is actually less than what you get on a GTX 970, or I think even most NVIDIA cards. Like, a lot of NVIDIA cards will have like a row of multi-layer ceramics sort of along the outer edge of the memory chips, and that's not really something you see on a lot of AMD GPUs off the top of my head. Like, usually AMD will have like one or two multi-layer ceramics directly behind the memory chip, but you won't get like rows of capacitors running around the like outer edges of the memory power distribution. So yeah, that seems to be more of like an NVIDIA design thing. But anyway, I had like, a lot of multilayer ceramics to use. So yeah, there. This one didn't because it's right next to this screw hole. I don't think I'm actually ever going to use this screw hole for anything, but also it's like this is ground, so I'd have to like insulate over it if I wanted to put a capacitor there, and it's just like, I don't want to deal with that. We have here, here, here. These got some extra multilayer ceramics here. Um, oh, there's a little one already that was there earlier from like the initial. And you can just about make it out over here. Um, and I also added some multilayer ceramics to the PEX power delivery. So that's like this over here. So yeah, there's a linear regulator on the other side of the board that lives like right over here, and yeah, that's the PEX power delivery. So I just threw some extra multilayer ceramics on there because like I had a lot of capacitors, so why not? It's not like I'm about to run out of them anytime soon, and if I did, I have a lot of dead GPUs that I could use for more. So yeah, anyway, so basically on the back of the card, every 0805 that was already on the card basically got another 0805, except these two, because this is where I'm measuring with the oscilloscope, and I don't really think like changing the capacitors, like changing how much capacitance is right at where the oscilloscope is hooked up, I think would kind of not be good for the measurement accuracy. Also, with the oscilloscope, I do have a 50 ohm termination at the oscilloscope. Anyway, so that's the back of the card, and then on the front, it's more of the same. And I forgot we're just going to get myself an extra layer. Yeah, so, actually I could have just drawn on the front of it doesn't matter. Anyway, on the front of the card, basically more of the same, except in this case, like, this one got, like, originally this was one capacitor, now it has two, and I accidentally changed my colors. So, yeah, like, originally one, now there's two. That one got an extra one. Obviously, I didn't fit one over here because there's this resistor, which, yeah, like that gets in the way. Over here, there's one. Here, there's two. Same issue here is like these pads are getting in the way, so I didn't add anything there. Added a bunch here and one over there. So, yeah, my goal of using every single 0805 that I salvaged off of that dead 7970 was achieved. There are no more 0805s left over because they got, like, well, a lot of them ended up in the VCore power delivery of this card, and everything else, like, everything that didn't get used for VCore or PEX just went into the memory power delivery. So what did that do to the voltage regulation? And, well, that's here. So this is the before. Right, this is how the card, like, it wasn't completely stock, but this is like the mildly upgraded version. And so you can see that like the minimums, oops. Okay, I'm gonna need a new layer. I'm just gonna throw that on top. So you can see that the minimums, worst minimum measured was like 1.505 volts. And on average it was like 1.509. With the peak to peak was like on average it was like 76 millivolts, but worst case scenario peak to peak was 91 millivolts. And this is all running 3D Mark Time Spy graphics test 2. So yeah, that's how it used to behave. And then here we have the upgraded version. And so minimums didn't really improve that much, right? We've got like average went from 1.509 to 1.516, so that's like a 7 millivolt improvement. The worst minimum ever like measured throughout the entire test also basically saw like it's like 8 millivolts. Yeah, we went from like 1.505 to 1.5137, which yeah, that's like 8 millivolts, almost 9. Not great. If you look at the peak to peak, it looks really good because we went from, like 76 millivolts down to 45, so that's like a 30 millivolt improvement. But that's because I basically crushed the overshoot, and the overshoot really doesn't affect overclocking very much. This is one of the, like, this is the whole, like, oh yeah, you can make like a huge difference to peak without really affecting the minimums, is the main reason why I don't do my oscilloscope measurements in AC coupling mode, because peak to peak is basically meaningless from like a overclocking capabilities perspective. because you can have a massive improvement in peak to peak, right? Like this looks like a really big improvement. We went like 30 millivolts on average reduction in peak to peak. I mean, worst case scenario isn't as big. That only improved by like 24 millivolts, right? We went from 91 to 50. Wait, am I screwing up the math on that? I am screwing up. That's a 34 millivolt improvement. So, okay, yeah, so both look like, a substantial improvement there. But in practice, we don't get like this isn't like because these are Samsung GDDR5 memory chips, so they do actually scale with voltage. If you give them more voltage, they clock higher. Um, a 30 millivolt reduction in peak to peak is not the same as increasing the minimum, like increasing the voltage by 30 millivolts. In fact, the overclocking improvement is equivalent to raising the voltage by like 7 millivolts, because that's the improvement that we get in the actual minimums, which is why I use DC coupling for these kinds of measurements, because this is like the memory chips care about this, and the memory controller cares about this. Though I think in this case it's primarily the memory chips that are like benefiting from the extra voltage, and the minimums really didn't just change that much, right? Like, so yeah, the memory, it does clock a little bit better. The card previously really struggled to go over 2 gigahertz on the memory for Time Spy. It now can run Time Spy at, I think, up to like 2050-ish. And Firestrike can actually run with plus 620 and like mild artifacting, whereas previously it wouldn't even make it through graphics test 1. So there was a slight improvement in the memory overclocking capabilities, but it's not like I've had some cards where they have like a huge improvement in memory overclocking, but those cards also usually started with a peak to peak of like over 100 millivolts, so the minimums go up by like 30, 40 millivolts, right, instead of 7. Um, so this really didn't make too much of a difference. Even though like the oscilloscope trace looks a lot cleaner and the peak to peak looks a lot better, ultimately the memory chips don't care about the like overshoot. That just really doesn't affect them. Maybe some other memory standards would care more. But yeah, GDDR5, especially, like, it just doesn't. It does not care about peak to peak. It really only cares about the minimums, and the minimums didn't really change that much. But it is worth noting that as you put more stress on the memory power delivery by running higher memory clocks, higher core clocks, higher memory voltages, the voltage regulation would actually get worse. So at, say, because this card comes stock at like 1.55 volts, which the oscilloscope is measuring as 1.54 due to how I hooked it up. So that's like a measurement error due to my methodology there. But like that error is consistent, right? Like the gap between the average and the minimums is what we care about, not like the average in and of itself. So that's not a concern. But the stock voltage for the memory on this card is like 1.55 volts. And where was I going with this? And these are Samsung memory chips. These can scale to like 1.9 or higher even. So yeah, like at those higher voltages, this might actually have more impact on the overclocking. So basically, maybe I should have done this testing with like a higher operating voltage for the memory, but the thing is, I didn't want to spoil myself on how the memory would overclock on this card, because I like. So yeah, like that's kind of the hard thing of like, well, maybe I should have done the testing at higher voltage so the power delivery would be under more stress. But then I would also know how the memory is gonna like overclock at higher voltages ahead of time, and I do kind of want to. Well, I want to save that for other content, so I haven't done that yet. Anyway, let's talk about getting more voltage on this card, because this is an NVIDIA GPU, and it's a 900 series NVIDIA GPU, so it's basically completely locked down. And then with the core, that doesn't really matter, because I've never seen a 900 series GPU actually scale with core voltage, unless it's well below 0 degrees Celsius. So basically, if you're on like air cooling or water cooling, raising the core voltage does nothing, and sometimes it actually makes things worse, is my experience. And usually the cards max out at like 1.22-ish volts or something, um, even if your temperatures aren't that high. So I don't like the 900 series very much as far as overclocking goes because they don't scale. Like 600 series, 700 series, those cards come stock at like 1.2 volts and they scale to like 1.35 easily. And some of them will scale even to like 1.4. And then there's 900 series where they come stock at 1.2 volts and they scale to like 1.22, maybe, which is really boring. So basically, whatever the card does at stock voltage is what it does on like max voltage. So I don't particularly enjoy these as far as like ambient overclocking goes. But the memory on them does scale, even on air cooling. And especially the Samsung memory scales a lot. So, extra voltage for the memory. The voltage controller on this card for the memory is this thing. And you might notice that the part number, the label on it is horrible. So, what this thing is this is a Richtech chip. And I know this is a Richtech chip from past experience, because Richtech chips just come with labels that look like this. So now for future, like in the future, if you see a chip with a label that looks absolutely impossible to look up using a search engine, it's a Richtech chip. That'll make your life a lot easier, because the way I figured out what this is, well, I looked at this, and it's like, okay, I know it's a Richtech because it has this horrible label on it, and I know it's a two-phase controller because this has two memory phases on it, and it's on a modern NVIDIA GPU, so it probably uses PWM vid, and so I threw all of that into a search engine, and that spat up a few different Richtech voltage controller data sheets, and I just sort of went through them until I found one with the matching labeling, and that one is the RT8809, and here is the labeling convention. Yeah. Like, this is great. You know what's really annoying about this? Richtech does actually manufacture chips which just have the full part number on them. So, like, they are capable of printing the full part number. Like, there's a bunch of motherboards where that use, like, a Richtech RT8120 for their memory voltage regulator. And it just has RT8120 on it. And then there's, like, then there's Richtech chips like this one, where you just have 08, and that apparently is the product code, and good luck Googling that. Good luck, because, yeah, that doesn't work. Basically, the only way to find these things is if you already know that they're Richtech chips. So for future reference, this horrible labeling convention belongs to Richtech. So if you have a chip that has a label like this, or with, like, an equal sign in it, then just like start digging through Richtech data sheets until you find one with the correct marking information. And the worst thing is, even like I don't know how you would like specifically use a search engine to find just this part of the PDF, right? Like that, like you do actually have to open the PDF up and basically look for this, which is ugh. So anyway, but luckily this didn't take too long. I think the only other chip that came up when I searched for two-phase Richtech controller was the RT8810, which I think is used for all like some newer NVIDIA GPUs, not 900 series. But anyway, so that's our labeling healer. And now then, let's take a look at the pinout of this chip, because that's how we're going to get our voltage control. And this is, actually, I'm not sure if it uses PWM vid. Well, they don't dual phase. Do I care? I don't really care. Yeah, I don't really care. Anyway, here we have the pinout. And basically, like, this pin and this pin is what we care about, and we'll get to, like, the actual, like, explain, like, the functional pin description. There we go. So VSET, output voltage setting. Connect a voltage divider from VREF to VSET to set the output voltage. And then VREF is reference voltage output. It's just 2 volts. RT8809AB generates a 2 volt reference voltage from the VREF pin to VRTN. This is just ground. And then we do have that last pin called RSet, output voltage setting. Connect a resistor from RSet pin to VSet pin. The output voltage can be switched 2 levels by driving vid pin. Oh, so I guess it has like an idle state only. So anyway, this is very similar to what you get on a lot of actual PWM vid controllers, like say a UP9511, where you have a pin. Well, you have a VREF pin, which spits out 2 volts, and then you have a VREF. No, what was it? You have VREF, and then I think VREF in. I can't remember the labeling, but there's a pin, and whatever the voltage on that pin is the voltage that the controller is set to output. So all we really need to do is we just want to raise the memory voltage. We don't want to lower it. I don't see any reason that you'd want to lower it. So we just want to raise it. These are Samsung memory chips. They scale with higher voltages. So all we really need to do is bring VSet closer to the value of VREF, right? Because VREF is at 2 volts. So let's take a look at the card. And our VSet pin is over here. And we know it's over here because if you look at the pinout again, you have this. Oops. Man, I should have just given myself an extra layer. It doesn't matter. You have this right here to indicate where the dot is, right, on the chip. And then, of course, you have pin 1. And conveniently enough, the silk screen on this GPU actually labels pin 1. And not all GPUs will do this. You won't necessarily have this little indicator arrow, which is why it's useful to be able to orient yourself based on the dot, because I don't think I've ever seen a chip that doesn't have the dot. But I have seen silk screens where you won't get the little indicator arrow, though you might get, like, you'll notice that the silk screen for the chip also kind of has that, like, corner over there. Anyway, so we have this pin over here, and this pin traces out over to this resistor, and then this resistor connects to VREF like that. Right, because the VREF pin is next to VSet. So, and the resistance between these 2 pins, so from here to here, is 1.63 kiloohms. And so if we want to increase the output voltage, we just need to reduce the resistance between these 2 pins. So that's very simple. You just connect a potentiometer right across this resistor over here. I mean, technically you could solder that potentiometer directly to the pins, but that's generally more difficult to do than just soldering across a resistor like that. And then, like, it doesn't really, and you just have one end of the potentiometer connect, like, the adjustable pin. Like, it doesn't matter. Like, you could have it the other way around as well. And you leave the third leg of the potentiometer just, like, hanging out in the breeze. That doesn't need to connect to anything, right? We're just using it as a variable resistor here. So yeah, that's all you need to do, and then you have the ability to increase voltage. Now, if you wanted to lower the voltage, you would actually connect, you could potentially connect this end to ground, and then you'd have the ability to lower voltage by reducing the resistance to ground. I don't know why you'd want to do that with Samsung GDDR5. In fact, I can't think of a single chip of GDDR5 where you'd ever want to do that. But I don't know, maybe you're... no, I actually cannot think of a practical application for this, but if you wanted to, you would just, like, either connect the potentiometer just to ground, or connect one end to ground and one end to VREF. Now, what I do a lot of the time with volt mods is I'll put a resistor in series with the potentiometer to limit the maximum voltage, but the maximum voltage that you can set this chip to is 2 volts, right, which is the output of VREF. VREF only outputs 2 volts, so the maximum output voltage you can set is 2 volts. And the thing is, the Samsung GDDR5 memory chips scale to some very high voltages, like 1.9 volts or higher even. And so in this scenario, I don't really see a point in putting a limiting resistor on this, because I think there's a decent chance the memory controller might die if you actually set the output voltage to 2 volts. But if, you might be able to run a few benchmarks before that happens. And I mean, I probably wouldn't do that with a GTX 960, but you might want to, max out a GTX 960 or a 950 or something. Or maybe you have a massive stack of GTX 970's. And to be honest, the EVGA ones aren't like it's not like these are particularly good PCBs, so I don't really, like if you were going for the absolute, like really trying to max the card out, and if you're on liquid nitrogen, the memory controller might actually last a longer at 2 volts than it would on ambient. So yeah, you might actually run into a scenario where setting 2 volts as the memory voltage wouldn't be the most insane thing, so I don't see a point putting a limiting resistor on this. But if you had like a GDDR5X GPU, where GDDR5X only really scales up to like 1.55, maybe 1.6 volts, there I would say it makes sense to have a limiting resistor to make sure that you can't so that you can't set the memory voltage above like 1.7 or something, because realistically you wouldn't be setting it to 1.7 anyway, right? And then the 2 volts, like it just means that if you do something stupid by accident, you don't accidentally blow up the GPU. But here, you might actually want to go all the way to 1.9 or higher, and so having a limiting resistor on this is just kind of, yeah, like, I wouldn't do that. Kind of pointless. Because you might end up in a scenario where it's like, oh, I need to take the limiting resistor off, and it's just like, why did you put it on then? So, anyway. And here's how my volt mod actually looks. So yeah, I just glued a potentiometer to the board. And then I have some very fine enamel-coated wire that just connects over here and here. Yeah, and then the wire is like bent around, so it doesn't make contact over here. You wouldn't. I'm not sure what this pad is, but we do not want to be connected to it. I can tell you that much. You definitely don't want to be connected to that. So, yeah. Anyway, so and the potentiometer is 20K. You could use a 10K, but with a 20K you get a lower starting voltage, because if you use a 10K, right, because the card comes stock at like 1.55 volts. If you use a 10K, I think it'll start you at like 1.6 something. With a 20K, it starts at 1.58, or like 1.57, something like that. Right, and that's just because this resistor is 1.6K. So if this resistor was like 5K instead of 1.6K, you'd want to use like a 50K or 100K potentiometer, but this is a 1.6, so use a 20K. If it was a 1, the 10K would make less of a difference. So, yeah. Also, if you wanted the ability to turn the mod on and off, you would just have to put a switch in series with the potentiometer, but I don't really see a reason to do that on a, zombie GTX 970. If this was a card that, like, I wanted to be more fully featured, then yeah, you could put a switch on it. So, but yeah, this is like a, GTX 970 zombie. I don't expect it to last very long, so I don't think it really needs a switch. So, yeah. I mean, I don't plan to intentionally blow up the card, but if it dies, then, like, I don't feel like this will be too much of a loss. As long as it gets some good benchmark scores before it dies. Should add that. If it dies before it gets any good scores, then it'll be annoying. Anyway, yeah, so that's the memory power delivery. I'd say the massive amount of multi-layer ceramics that I added to this were not exactly the most necessary thing. Like, if you're thinking of modifying one of these GTX 970s, I don't think I would go, oh, I'm going to slap an extra 0805 on every single 0805 that the memory power delivery already has. The biggest improvement, I would say, was just from the 560 microfarad caps that I added. So, and that takes significantly less time and effort. I will point out that, like, if you're wondering why this capacitor is at this angle, it's so that it's not super close to this screw hole. Also, if I'm not mistaken, the stock cooler for these cards actually uses this screw hole instead of the outer one. And yeah, well, I didn't want the capacitor to be over the memory chip. Not that that would really make a difference. It would just make it it would add height to the capacitor, and I didn't really like the idea of that. Like, ideally, I would have wanted the capacitor to be over here, but the way these pads are set up, yeah, like, that's not going to happen. Not without having the legs be, like, super, super long and awkward, and it's just like, oh, well. So, yeah, so basically, if you're thinking of, like, oh, I want to upgrade the memory power delivery on a GTX 970, I'd say add some polymers. That that I'd say made most of the difference. And then the multi-layer ceramics, if you have them to spare, like, sure, throw them on, but, like, I don't think I'd go this far. This was really a case of, like, I had an entire 7970 worth of 0805s. I was going to use every single one of them. Because, yeah, I don't, like, the funny thing is, in the past, I'd, like, leave leftover multi-layer ceramics on my desk from, like, when I used salvage capacitors from cards. And the thing is, I just end up throwing them out because at some point like later down the line, it's like I don't know if these were from input filtering or output filtering. So it's like, are they rated for 16 volts or are they rated for 6? I don't know. In the bin they go. So at least that's what happens to the salvage capacitors. Because obviously, if I buy multi-layer ceramics, then I know exactly what they are, and they're labeled. But yeah, like when I pull capacitors off of dead GPUs, they tend to end up just lying around on the desk, and then they eventually get thrown out. And so this time around, I was like, well, I'll just put them all on the card, and they won't get thrown out. So yeah, that's it for this video, and hopefully you found it somewhat interesting, if not particularly useful. And the GTX, like, I'll probably be doing an overclocking live stream with this GTX 970 just on air cooling pretty soon. So I don't know. If you find that interesting, you might want to, like, subscribe for that or something. Anyway, that's it. So thank you for watching. Like, share, subscribe, leave any questions, suggestions down in the comment section below. And if you'd like to support what I do here with the channel, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store where you can pick up shirts, hoodies, posters, you know, the usual YouTuber merch. And I've also got a Bandcamp. There's a link to that down in the description below as well. And that's it. So thanks for watching, and goodbye.